I want take this opportunity just to confirm that we will have our recovery lecture next week on Wednesday, as usual, from 8 to 10. Okay, this is my proposal. And that's all. Okay, after this 15 minutes silence, we can start with our lecture. So, breaking the silence. Um, okay, and I also want to announce to you that I will drop all the video available in the first weeks, and I will leave only the last 2 weeks videos, as I told you at the beginning of this uh, lecture. Um, so I will share my presentation, and I essentially continue to talk about what we have done. Uh, Essentially, we are talking about the construction of the aerodynamic force matrix, and we have studied in details each part of this operator. We have essentially a feedback here given by the aerodynamic force, taking into account the deformation of the structures, of the aircraft structures, and then we have modeled this feedback, decomposing the aerodynamic feedback in 4 parts, and we are actually studying the last sub-operator, E1. E1 sub-operator is a special operator transforming the model coordinate here into, and the number of this model coordinate is equal to the number of the mode, and into the normal wash, which is actually the input of the potential flow, the steady normal wash to the aircraft. We want to define this operator in Laplace domain, and so this operator is something like a matrix operator, depending on the Laplace variable, such that as applied to the model, the Laplace transform of the model Lagrangian vector, this matrix multiplication will give the Laplace transform of the downwash or normal wash vector. These two vector, state space model vector and the downwash or normal wash vector, are both depending on the Laplace variable, since they are representing the Laplace transform of the time domain quantity, related quantity. Okay, so we have subdivided this. This is a very key point in the fluid structure interaction. The fluid structure interaction is essentially based on 2 levels of interaction, this here and this here. In this level of interaction, you have the output of the structure, the displacement, or something equivalent to structure displacement. And as a first step here, you want to transform this wall displacement or structure displacement into an aerodynamic steady boundary condition. And this is just we are doing now at moment. Another level of an interface is the second phase of the interface, fluid structure interface, is the step whenever you have the aerodynamic force and you want to apply this aerodynamic force onto the structures, as depending by the structural displacement. Okay, so we are talking about this phase here, and so we have represented we have to represent the body displacement in the wall interface into a fluid displacement as well. Okay, so this body is the projection of the body wall velocity into the normal to the body, and both this quantity are unsteady component because the body velocity BB is a sum of a rigid body translation given by the aircraft. So these boundary conditions are therefore boundary conditions which are uh, mm, referring to a translation of the aircraft, not to another kind of maneuver, a complicated maneuver. So we have a rigid body reference motion plus the relative motion with respect to this body frame of reference, which is actually the deformation. And in particular, here we have the derivative of this deformation because we are representing the velocity. So this VB is the sum of these two quantities just represented here. And as a second step, as a second important step, we have to define also the normal to the body as a varying quantity, varying with the deformation. And so we have expressed the actual value of the normal as equal to the value of the normal in the under form of configuration like n0 plus a flexible or body flexible dependency. So just a normal correction, take into account the flexibility of the body. So this is the, in red here, we have the deformed normal in red, and here we have the original normal. So this difference vector is expressed here as a function of the model coordinates, because this difference vector is essentially dependent on the deformation. And considering the expression of the normal, we achieved to represent this correction in terms of model coordinate. And this is here just the final result of this developing. As a final point, we have applied this dot product just to obtain key. So we have this product developed, and we have a steady component plus an unsteady component. Now, I have a very relevant point to present to you. This is the point of the point of about the steady component. The steady component of the boundary condition indeed can be avoided because we can avoid the steady contribution in stability or flutter analysis because in linear framework, in linear analysis of framework, these steady terms are not influent. And this is a very, very general point in the stability, in the linear stability theory. Influent. Let me show you this point. This means the following. If you are studying a flutter analysis of this wing, with 0 angle of attack, or the stability analysis of this wing, the same wing with not 0 angle of attack, the result of the stability analysis is the same. So the same stability scenarios, because the difference between these two conditions is just a steady force as applied to the wing. Okay? The same stability analysis. And this point is a key point in structural dynamics and in fluid structure interaction, or in general in systems theory. Okay, this is the same point of consider the system, mass, spring, and consider this system, spring, mass, the same spring, the same mass, but including the gravity. Mass plus gravity. Okay? If you consider the mode of vibration, in other words, the poles of the system, you have that omega, you have that the poles are equal to plus minus j k on m. So you have an oscillation around this level regulated by these two poles of the system, giving you an harmonic oscillation. If you include the gravity, you are able to change your reference steady solution or stationary solution, but the oscillation around the new steady solution is exactly of the same time with the same poles, just equal to plus minus j k on m. So you have the same pole here, the same poles, the same vibrating characteristic, but here around zero and here around a not zero solution given by the presence of the gravity. Okay? In fact, in this case, you have an equation like this. In this case, you have an equation like this, giving you a solution that as a steady value, the x steady displacement are equal to minus gm divided by k. So here you have an oscillation around to this amplitude, this level of solution, and here you have the same here. If you consider zero angle of attack and eventually a symmetric airfoil, and you see what happens in the steady state, you have zero displacement, zero deformation, because the overall aerodynamic force as a overall steady balanced field of pressure around the body. But in the other case, when the angle of attack is not equal to zero, you have not zero displacement solution, just like here, the displacement given by the weight, plus a vibration around to the solution, okay? But the poles, which in this case are not margin poles, but they should be something like that in the elastic system. You should have hopefully stable poles like this. The poles that do not change in both the cases. So you can directly assume for the aerodynamic, a aerodynamic force solution which is steady component free. And this kind of boundary condition is are the potential boundary conditions able to give you steady solution, not time depending. So the only unsteady component, the only unsteady boundary condition are here, that given by the presence of this term, which are the time depending term. The only time depending term able to give you unsteady boundary condition. Okay, so we are, from now on, we will consider this term as equal to 0, but these terms are not equal to 0, but can be avoided in this case if we are interested to compute linear analysis only. The general motivation of this point is given by the following, and this is very popular. If you consider demonstration of this, the demonstration is very easy. Consider a system, a general system like x dot equal to ax with 0 steady solution. Okay, so the steady solution is the solution such that you obtain when x dot is 0. Okay, and if A is not singular matrix, the only steady solution in this case is 0. Okay, so what about the vibration around to this steady 0 solution? The free vibration are given in this case by the eigenvalues, eigenvector of a matrix, the eigenvalues lambda, the eigenvector u, and so obtained by, in the usual way, the standard eigenproblem, by taking the determinant of lambda I minus a equal to 0, and then determine the eigenvector by solving the following. Okay, and this is standard. After that, the free solution x is given by the combination of the eigenvector, obtained eigenvector, by e to the power lambda n t. Okay, and this is your system. If the real part of lambda are in the left half plane, the system is stable, and so on. But in particular, the 0 solution is stable. Now, if you consider a static load, like the gravity, or like an angle of attack, a steady loading field to our elastic system, consider a steady load like x dot equal to ax plus u. This u is steady, not depending on time vector, not depending on time load. So you are imposing this load. The steady solution, you have a steady solution like x steady solution. You have just to put the derivative as equal to 0. So you obtain the steady solution like minus a to the minus 1 applied to u. This is your steady solution. Okay, now look, let's study the dynamic around our steady solution. In the case of the simple harmonic oscillator here, it means the following. Let's study our vibration around the solution obtained by considering the gravity force here, okay? It's just the same. And so we introduce in the state space a relative motion in the state space with respect to the steady solution. So consider this vector C. So you have, imagine to represent our solution in the steady, in the state space. You have the first state space variable, the second one, the third one, and all the other. We cannot represent in the physical space because typically we have more than 3 state space variables. And a point here is your steady solution. This fixed point is x steady. So you found that this is a stable solution. So if you, for example, consider this steady load and this here as initial condition, is the system is stable, you should have something like that. To regime, you have this, okay? And this is the trajectory in the state space. State space trajectory. So we don't have the trivial solution, the zero solution. Not. We have this special, not zero steady solution. What about the dynamic around the new steady solution, which means the aircraft with an angle of attack in our case, okay? And we have the following, we have that the dynamic, this point here, is decomposed as the following, here, is decomposed as, look, this final x solution point is equal to the summation of your steady solution plus this here, which is the relative motion with respect to the steady solution for a vector like C. So what about the dynamic of the new vector C? Simple. Substitute this to our equation here. Substitute your x variable here, and you have that x dot, which is x steady dot, but this is 0 because steady solution is not depending on time, plus c dot is equal to a applied to x, but x is x steady plus c plus u. Okay. Oh, very interesting, because we have c dot is equal to a on, of course, the matrix is a linear operator, so we have a applied to x steady plus a as applied to c plus u. But by the definition of a steady solution, these two quantities are actually canceling because of the definition of steady solution, and therefore you have, for the relative dynamics with respect to the steady solution, I mean the vibration around the steady solution, in other words, it's regulated by this equation. And this equation is identical to this equation, which is the equation around the zero solution. So the same matrix A, the same eigenvalues, the same eigenvector for describing the dynamic. So, ladies and gentlemen, from now on, I hope you are convinced of this fact, because this is one of the mystery of student. Okay, the steady solution doesn't, in linear system, linear, here, linear. We applied the concept of linear operator A. In the linear system, the vibration, the dynamics around any steady solution is actually the same. For this reason, the angle of attack for linear elasticity does not affect the stability, period. Okay? Okay. Okay. I feel better. Now, all this parenthesis is just to allow this point. At the end, so at the end of this parenthesis or bracket, we have this formula for expressing our boundary condition. This is, now skip our bracket and go here. Here we have that this summation, which is this summation here, is giving us the normal wash, which is on the fluid side. The normal wash as a function of x and time is equal, with the fluid side, is equal to summation r term q dot r and 0 the dot psi r minus u infinite I dot delta n r vector. I have just repeated this this here for you, and now I forget this QR. Okay, now let me undimensionalize this equation, because this here dimension is the velocity. So let me divide everything with respect to a reference velocity, like the free stream velocity, u infinite, and then cancel this. Okay, and localize this space continuous formula. And localize means, please calculate this expression at the center of a panel. So you have a value of key for each panel, like for example key J. This undimensional value will be referred like a key bar. Key bar. Okay, so key bar J without X, because we have localized this in this point in the panel, the point with coordinate X, J. Key J fluid side is equal to, this is a structure side, is equal to summation of, this is a modal coordinate, So the summation is running from 1 to the number of mode included in the analysis. And this is the local normal in the undeformed configuration, but evaluated in the xj point, because all the space quantity are located in the xj point. Dot, and this here is the component of the mode shape, r mode shape, but again in the xj point. This is the meaning of this localization procedure. Here we have divided by u infinite, and here we have minus I, the unit vector in the x direction, by delta n. This delta n is a quantity depending on the mode, but is also depending on j, because remember, here you have all quantity for delta n localized in a point. So you have to calculate this local vector or this mode shape in the xj point, and therefore this quantity is dependent on xj as well. Multiplied, all this is running with r, summation in r. Final point, take the Laplace transform of this, and so we have the Laplace transform of key in the j point is equal to summation of r from 1 to n mode. We have a q dot, so we have s by Laplace variable by q bar tilde. This was bar model coordinate, because these are model coordinate. Blah 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 r and 0 in the xj point, psi dot psi r in the xj point minus I dot delta n r in the xj point by q bar tilde. And so we can group this q bar r outside this bracket, and so we have a matrix, excuse me, divided by infinite. We have a unique matrix depending on the index j, the index r, and this matrix is depending on s, and also by u infinite. If you apply this matrix operator to q bar tilde, you obtain key, and this is the boundary condition operator we were looking for here. This transforming our q quantity in our key quantity, and then the key quantity are transformed to the psi quantity by E2, and the psi quantity, the velocity potential, are transformed into Cp by the E3, and the Cp are then projected on model shape, on the mode shape, so obtaining the generalized force. And this is the story of the aerodynamics. This is the structure of the aerodynamic operator. Okay, as you can see, the unsteadiness of the aerodynamic operator is given by the dependency of these matrices by S. And at the end of this novel, we have finally here a we have finally here key like vector like E1 matrix applied to Q vector. This matrix is not square matrix, but it's rectangular because the number of component of key is equal to the number of panel. We have M panel and we have M panel and N modes in the analysis. Look at this dependency on S. This dependency on S and on the flight parameter U infinite is defined by this ratio. So again, you can also consider in this ratio a reference length like L dividing and multiplying by L. And then we have again a unique undimensional Laplace variable P, including the dependency on the Laplace variable S and the free stream U infinite. Okay, so in other words, this operator is depending on P. And now let's recap together all this dependency of the aerodynamic operator. Let me have a final recap on our matrices. We have the following. Recap. Oh, yeah. Oh, recap. We have this. On the left hand side, and on the right hand side we have the aesthetic dynamic as composed by a factor, a constant factor given by the flow characteristics. This is the dynamic pressure, and then we have E4, E3, E2 and E1 applied to Q bar again. So my question is, how globally this matrix, this final matrix, is depending on P? So let's recap this consideration. We have for E4 no P dependency. In fact, we have that E4, the component NM, and E4 is just a projection, so you have that this is equal to minus the integral on the final surface M, normal, evaluated in the M point, X M point. This is an N0 normal, the normal in the uniform configuration, projected to the N mode shape. Okay. Yes. So we can see here time of frequency or Laplace variable. No dependency. Next, E4. Okay. E4, E3. E3, yes. E3 is depending on P. And in particular, we have that P dependent. In that we have E3, the component NM is equal by the the Bernoulli theorem, we found that this is equal to minus 2 by delta nm plus the matrix of the finite difference d mn, and here we have just a p. Okay. Next, E2. E2 is probably the more complicated matrix, because in E2 we have the complicated story of the wake, the delay of the wake, blah blah blah, and so on. And so this is p dependent. This is terribly p dependent. And this dependency is given by the following. We have that E2 is equal to y to the minus 1, matrix p dependent y, multiplied by the matrix of the source B. And this Y is a matrix like delta Mn, the Kronecker symbol, minus the matrix of the doublet Mn, this is N, excuse me, and then we have the matrix of the doublet but on the wake. Let me use M and L like life. So we have M, N like nipple, S, N, the stupid matrix, nipple and life, and E to the power P minus P by the n-dimensional distance between the x point of the wake minus the c point at the leading edge. And this is the y matrix to the minus 1, and this is the term M like Milan and L like life to be multiplied by B. Okay, this argument of the exponential in the dimensional variable is minus s by x by x in the wake point minus x in the trailing edge point divided by u infinite. This is the dimensional in Laplace variable. This is the undimensional by introducing p. Okay. The last but not the least operator we have just evaluated is E1, this function of p, is p dependent as well, and this operator, we have just found the operator here, and this operator is equal to, for a component, the E1, for example, JR terms, function of p, is equal to p by psi r, and here we have the mode evaluated in the xj point, dot the normal, and then the formal configuration evaluated in xj point again, divided by a reference length we have used as a reference length L, and next we have delta n r in the xj point dot the unit vector I. Okay, this is the term JR. Conclusion. When you take the product E4, E3, E2, E1, and these three are function of P, 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 you obtain a matrix, a global matrix E, which is function of P. Of the which kind of dependency? Now you have the answer. The dependency is something like up to P to the power 2, because we have a P here, a P here, and a P here, but you have also this exponent here, plus, excuse me, so we have this plus something E to the minus P. Okay, minus P by C. So the dependency is, I have a comment on this. I expect two separated contribution. After this, I expect two separated contribution which are a polynomial dependency up to second degree, B, a transcendent is mathematic, transcendental is philosophy, okay? A transcendent dependency of type e to the power s minus p c. Okay, and what a polynomial dependency up to second exponential degree mean? What does it mean? It means that we expect mass damping / stiffness equivalent effect. Are you in agreement with this? Are you engineering or not? I expect by the aerodynamic equivalent mass damping stiffness effect. I expect this. And this is the deep motivation of this expectation. All the theory we have developed has given as a result this kind of expectation. Okay? And in fact, somebody, did you ever hear something like equivalent mass, aerodynamic equivalent mass, or aerodynamic equivalent stiffness or damping? In general, the aerodynamic mass effect. Did you ever heard this or not?
In Professor Marino's course.
Okay. And this is the demonstration. Okay. When you have a body vibrating, I'm going to have a break with you. When we have a vibrating body in a flow, you are actually moving the fluid mass around your body, and so you have an effect of an added mass. But you don't have only this effect. You have also an equivalent stiffness mass and an equivalent damping mass, an equivalent damping effect. And this is predicted by our mathematical model, because in Laplace domain we have found that we expect a dependency up to the second order with respect to P for the dependency of our aerodynamic operator on P. Okay, we don't have an analytic description of this second order polynomial dependency because we don't have a coefficient, a matrix coefficient multiplying P squared plus a matrix coefficient multiplying P and plus a matrix coefficient multiplying nothing, plus a matrix coefficient multiplied to e to the power. We have all mixed, but we know that inside there is a dependency to the P to the power 2 up to, not to the power, not up to P to the power 3, but only P to the power 2. This is our expectation within the unsteady potential flow theory. Okay? And I stop. For a break. No question, everything is clear, no problem.
Professore, giusto una cosa, l'operatore chi noi l'abbiamo definito a prescindere normalizzato rispetto alla U infinito oppure
Allora,
una cosa...
innanzitutto si parla inglese, seconda cosa, chi non è un operatore è un vettore,
Un
è un vettore di
scusi.
stato che colleziona la derivata normale del potenziale in ogni pannello, cioè la normale della velocità del fluido in ogni pannello, al centro, tutto discretizzato.
Sì.
Questa quantità è dalla parte fluido, è una quantità che uno assegna quando deve risolvere un problema di flusso potenziale. E chi gliela dà? Gliela dà la struttura che si muove, perché nell'interfaccia uno dice guarda che questa quantità, componente normale della velocità del fluido, è uguale alla componente normale della velocità del solido. Interfaccia fluido-struttura. Interfaccia 1, quella a destra del loop chiuso, quella che dalla struttura va verso l'aerodinamica. Ok?
Sì, sì.
Quindi questo chi è un vettore che entra dentro l'operatore E1 e E1 gli restituisce, chiedo scusa, entra dentro l'operatore E2 e E2 gli restituisce il potenziale. Questo chi proveniva dall'operatore E1 che è applicato sulle variabili modali, che sono indice di come si sta deformando la struttura, E1 applicato sulle variabili modali da chi?
Sì.
Va bene?
Sì, era giusto perché poi dopo noi quando è andato a scrivere la relazione dopo ha normalizzato tutto rispetto alla U infinito, quindi era semplicemente se
Sì,
noi già
poi diventa
noi lo
chi
definiamo
segnato quando divido per
normalizzato.
infinito. Qua diventa chi segnato quando faccio qua, quando faccio questo è chi, quando divido tutto per infinito.
Ah,
Quindi
ok.
questo qui è
Sì,
ancora
ok.
dimensionale.
Sì, ok. Avevo copiato male il simbolo, scusi. Grazie comunque.
Niente. Ho detto questo qui, ma non condividevo lo schermo, per cui non ho detto niente, però vabbè.
Sì, vabbè, però
Ha
l'ho seguita.
capito che volevo dire?
Sì, l'ho seguita poi dagli appunti sul foglio.
Ok.
Scusi, posso farle una domanda? In inglese forse. When we evaluated E4, the matrix E4, why we did not consider the normal dependent from the time as well?
Yes, because um, this is I need time for answer to this question. However, if you consider this point together with the point that also the domain of the integral is time dependent, you have into the integral, you have n as dependent on time, but you have also the surface of integration of the integral domain is time dependent.
Yes.
We told that the domain of the integral are practically time independent in the case of E2 matrix. And this is true, but we did not discuss such an integral in the case for this E4 matrix, but in the E4 matrix you have in the same way surface moving. Okay. Then if you consider the motion of the surface together with the fact that the normal is a normal actually moving together with the surface, because the normal is the normal referred to the moving surface, which is the boundary of the integral. Okay, if you consider this fact, you have that the integral of the actual normal in the actual domain is identical to the integral through the undeformed initial domain having the undeformed initial normal.
Okay.
Okay.
I have an idea now. Yes.
Okay. let me write this for you.
Yes. But it's more clear, I have to say now.
Your question is correct, but also my answer is correct. But it's not easy to show you with the present. Can you see the screen? No.
Yes.
You can? Okay.
Yeah.
I'm telling the following. You have to perform this integral on a panel, and you have a panel in undeformed configuration 0, and you have in that panel n0, and dot projected to this, and you have the CP. The CP is constant, so it's outside. Okay. Okay. So you are not considering this. You are focusing on this integral. Okay. But this integral is, you have that this integral is equal to the integral in the deformed configuration with the deformed normal, not n0, the field of the mode ds. Okay? And therefore, this, which is the quantity you are interested on, indeed is equivalent to this. And therefore, you can consider that 0 normal together with the 0 surface. And this is consistent.
Okay. Yeah, yes. It's more clear now.
Because indeed, all the integral on the surface, all the integral are material integral in the sense they are performed on the surface made by the same material point. Okay, are following integral, are integral following the body during the motion. Okay, and therefore you can take directly the integral in the undeformed configuration. Okay, it's not easy to eat this hot potato.
Yes, this is the most I think precisa, non so come si dice, rigorosa. This is the most rigorous demonstration we can get, or there is something more precise?
The demonstration is here. So this related to this. This is n0, and n is, remember, g1 cross g2 in the S. S0. Okay. And if you remember your theory on calculus 2, analisi 2, this is the element of surface, and probably the professor called it square root of, if I remember well, EF minus D, dx dy, and this is the element of surface. This is exactly the element of surface. The normal has the same meaning of the element of surface. So if you consider your domain in deformed and undeformed configuration, this is the element of surface undeformed, and this is the deformed one. Okay, your material coordinate are deforming, you are varying this, but the value of the integral is the same because you are lucky and you have direct, with this normal here, you have directly the expression of the element of surface for changing the coordinate. Ta-da.
Okay.
Is something, this is the light. Is the light? Si è accesa la lampadina? No.
A bit, se un po' sì, cioè dovrei andarmelo a rivedere.
Questo è l'elemento di superficie nel cambio di coordinate degli integrali di superficie.
Sì. Sì, ok. Tanto poi la forma modale resta quella.
E quindi tanto vale che prendi questo. Stai qui deformato, tanto vale che prendi questo, che è quello in deformato. Tanto è lo stesso.
Ok, sì.
Ok?
Penso che sia accesa.
Ok, dx di epsilon is equal to... Che cos'era? Come lo chiamavate voi? Questo qua è proprio la radice quadrata di EG meno F. Com'è che si chiamava?
No, non lo chiamo. Il Jacobiano, dicevamo, era.
Sì, ma lo jacobiano però dell'elemento di superficie, non dell'integrale di volume. Integrale di superficie è particolare.
Oddio,
Ok? Quindi
ma non mi ricordo.
dx1, dx2, ok? Dove qui questo è 1, cartesiano, è l'elemento di superficie, che moltiplica 1. Quando vai a coordinate deformate attuali, metti le due coordinate dx1 e dx2, ma ci devi mettere questo.
Sì, mi pare lo chiamavamo comunque Jacobiano, mi pare anche in 2D.
Ancora
Non so se mi, non so se mi
questo è
sbaglio, ma
proprio
mi pare
il
che sì.
jacobiano. Tanto
Ok,
vale quindi che lavori qui.
ok. Sì, va bene. Vabbè, il Jacobiano è proprio la normale,
Sì, esattamente.
il modulo della normale.
Sì, esattamente.
Ok,
Ok,
grazie mille.
prego. Okay, so let me continue our lesson and okay. Okay, so by our general theory, we expect this kind of dependency. Okay, now Tiedemann to Dorsen. Together with other guys like Glauert, von Karman. So he considered a straight airfoil like this. X u infinite, a very thin airfoil with a chord from minus b by 2, c by 2, excuse me, minus b plus b. So a straight airfoil. And so a simplified, very simplified domain. So the geometry is not general, is the limit of, you take an airfoil and take this thickness going to 0, tau going to 0, and so you have a straight airfoil, simplified domain. So your surf SB domain and your S-wake domain is really easy in this case. So he tried to calculate analytically all the steps E4, E2, E3, E1, and assuming for to the flow, the source solution G, like minus the logarithm of x minus x star divided by 2 pi. This is the elementary source solution, and this is useful for the E2, for developing your potential theory with the boundary. You need to know the elementary source solution. So Theodorsen worked on this, and Theodorsen solved analytically this problem. Analytically. And what about the result? The result was the following. This is our equation in time domain for an airfoil. So NB, note that for Theodorsen theory, the two Lagrangian coordinates Q1 and Q2 are not the model coordinate. But they represented Q1 the heave motion H, so the vertical motion, as I told you past week, the heave motion in a point, 1/4 point, vertical motion of 1/4 chord point, and Q2 is the pitch angle alpha. And if you develop the theory assuming these two model coordinates, you may evaluate E4, E2, E3, E1, and the final matrix. And this is the result, guys. Look here. This is the equation of motion in time domain. You have your dimensional lift per unit length, which corresponds to h. This is the Lagrangian variable corresponding to the heave motion, and here you have the aerodynamic moment, which is the corresponding variable, Lagrange variable, to the pitch degree of freedom. So these two generalized forces are expressed by Theodorsen as a function of the motion. And this is the final Theodorsen formula in frequency domain. Frequency domain means for S equal to j omega. So we have a dependency of the lift on omega and on the Fourier transform of heave and pitch. Okay, what did we expect by the general theory? We expect a polynomial dependency with respect to S up to second degree, and also a transcendent depending of type e to the power something p something. And this was just Theodorsen obtained by his theory. And note, we have the lift, which is decomposed by two parts. The first part is a part which depends to the frequency up to a power of 2. Here and here, and then a power 1 here. So in this first part here, we have something equivalent to a aerodynamic inertia or aerodynamic mass effect, but we have also an aerodynamic damping like this, because we have j omega. And but we don't have only this part. We have also this part here. And this part here, we have, again, the same quantity, like h0 is the vertical displacement of the origin of the axis, which is at 1/4 chord, okay? Oh my God. Okay. And we have this, but we have this special function like this. We have a function c, which is also known as Tedorsen function. And this Tedorsen function is a complicated function of omega. It's not a polynomial dependency, but this function is a transcendental function of omega. Note that in the moment we don't have this function c, well, we don't have c just because we have reduced our load on this rigid body, assuming as the center of this load 1/4 of the chord. If we move and decide to consider not this point as a reference point for the load, but another one, and so if you want to reduce your aerodynamic load around another point different by this, you will have the same force L, but a different moment, which is the previous one plus the lift multiplied this lever from here to here. And so you will have C also in the moment, of course. Okay, and as you can see in this formula, the moment as the aerodynamic moment ma with respect to the 0 1/4 point is an aerodynamic moment having only term power of omega. Now, this term here are also known in the literature as irrotational term of the lift. Irrotational. Or irrotational contribution of lift. This is the lift force. And this other here are the rotational part. Do you have in mind a motivation of this definition? Why this is irrotational, this is rotational? Why is rotational the part including C, the Tedorsen function, and why the other part, the part proportional to the power of omega, is irrotational? We are referring to a rotational part having in mind what? Which is the part of the flow which is rotational or rotational?
The wake.
Yes. And what? And which is the contribution of the wake? The contribution of the wake is exactly arising. It is just giving the famous exponential term like this. And this term in the general theory, this term, we have focused here. So where is it? This term here is the source of rotational contribution in the flow, because this is the term responsible of the delay induced by the wake. Okay? and so we have just now an idea what happens, and therefore now if you consider your exercise number 2, the test of your exercise number 2 here, okay, we have that this is the formula I have presented, and this is the expression of C, CH. C is a function of omega, B, and U. This means that essentially, C is depending on the structural number, is dependency on the reduced frequency. How? Did you ever hear? Did you ever hear the Bessel function in your life? Yes, no, maybe. Which is the answer?
Yes, with
yes.
Lombardo.
Concerning what? Concerning the signal theory with Lombardo. Okay. So you have that these two are the J0 and J1, Y0 and Y1 Bessel function, J and Y. You can compose with the Bessel function the Henkel function here. So these two are the elementary Bessel function. You can build, this is the unit, imaginary unit. By the imaginary unit, you may build this Henkel function. And with the Henkel function here, you can build your Todorson function. Okay, so the analytically, not considering panels, but considering space continuous aerodynamic, you will have as a limit concept not a e to the power, but you have Bessel function of the frequency, of the reduced frequency. This is the result of the theory. For demonstrating analytically this theory, we need probably weeks of lessons, okay? But I prefer to present to you the general theory, which is discretized in space, and then announce to you that if you have elementary geometry for wing and wake, like in this case, for two-dimensional flow, you may have analytical solution like this, okay? And therefore, assuming this complicated function of k, you have finally here our equivalent formula like E, excuse me, okay, I have to catch this. Let me, okay, let me use this. Okay, and excuse me, okay, so this is L and M. You can group everything multiplying H, everything multiplying alpha, for lift here. You have lift something multiplying alpha. Multiplying alpha, you have term like this, H like this. This is multiplying H. This is multiplying H. Where is it? Okay. Okay, and the rest is multiplying alpha, 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 and alpha. So you can organize all this formula in a matrix like this. And ladies and gentlemen, this is the analytic aerodynamic matrix for this kind of flow. And this formula is exactly the formula giving you generalized force in Fourier domain are equal to generalized matrix depending on omega and U infinite apply to your state space vector, which is at the moment given by h tilde and alpha tilde. Not model coordinate in this theory, but physical, in quote physical. Physical in the sense that you have displacement and rotation. And this 2 by 2 matrix is exactly this 2 by 2 matrix. And you can see clearly the dependency on omega, analytically by omega and u infinite. Note that this k is, please, omega b by u infinite. Okay, and in our exercise here, number 2, that I am going to assign to you, we have our section airfoil. We have our structure, simplified structure, this here. We have this equation. We have undimensionalized this equation with this undimensional group here. We have the lift, we have the moment. We have also our Theodorsen theory for lift and moment. You can undimensionalize your L and M. And at the end of the story, substituting this inside the equation in Fourier domain, you have this, and then assuming this, we have this very, very final formula. And what is this? Oh, what is this? Well, I don't know. No, you know. This is our final system. And this should be the system ready for studying the stability. But you have a problem, Houston. Your problem is that this is your characteristic exponential here. You see here p to the power 2. P is the n-dimensional Laplace variable. P to the power 2 grouped in a unique mass matrix, including structure and aerodynamic, the part of the aerodynamic expressing mass. You can include this aerodynamic mass contribution together with the structural mass contribution. You have a damping given by the aerodynamic, okay, Houston, and you have a stiffness, Houston, here. Okay? But unfortunately, you have a part depending on P, which is not in a polynomial form. Ah, shit. Because you have the Theodorsen function. How we can do? We could solve this pole problem by taking the determinant, not having a standard polynomial equation, but a transcendental equation. If you take the determinant of this, the determinant, and develop this determinant and impose to be 0, you will have an equation for the poles, but this equation of the poles is not polynomial as a standard in the linear theory. What can we do? Let me present to you a possible solution for this problem. Let me cut again this solution here and put this equation here for explaining you this point. Oh, stupid. Okay. Take this equation. And no gift, please. Here, we have a system of this type. Look, we have a system of this type. We have P square by a matrix A. This is A. You have plus P by another matrix B. You have a matrix C. And you have a matrix depending on P. You have a D depending on P as well, in a complicated way. This is your system in Laplace domain, in n-dimensional Laplace domain, applied to a complex vector, something strange, but I don't know, W equal to 0. Now I want to focus to the point that this exactly equivalent to have for a dynamical system. We are facing the deep point of the elasticity. These are the motivation why we have a specific course on this issue, right, guys? Okay, guys. So when you have a linear system, a standard linear system, you ensure the stability studying this eigenproblem. Now we have P instead of S. Okay, no problem. You know. And here, what kind of time domain equation we have? We don't have a explicit, we don't have presented an explicit time domain equation. But if you see this, Laplace, this Laplace representation of your system, this system is exactly this system here. If you go back to the time domain, you should have something second derivative, first derivative, a stiffness of the state, and here, what happens when you go back in the time domain? Having a quantity depending on P by a quantity again depending on P. When you take the inverse Laplace transform of this part, you have a product of something P dependent with something P dependent. So in time domain, you have, what do you have in time domain? When you have a product, you have a convolution integral. You remember this? When you have a product between two Laplace depending quantity and you come back to the time domain, the product in Laplace becomes an integration integral, and a time convolution integral. So your original time domain problem is a differential integral problem. You have derivative here and you have an integral here. And this is the double phase of, you have a double of the model. In one phase of the model, you have this Laplace domain version with a part complicated as a function of P, not polynomial. In time domain, you have a differential part corresponding to the rotational part or the structural part, and you have an integral, a time integral, specifically, you have a time convolution integral in the rotation corresponding to the rotational part here. And so you have, as time domain version, you have a integral differential equation. So you have an integral differential equation in time domain, and you have a polynomial or a transcendental equation in Laplace or frequency domain. This is the final conclusion of this story. I have only a point for you to be demonstrated, and this is the following. In the theory, in the standard theory of the system, you discuss the stability and you are convinced that the stability is regulated by the solution S of this equation, because you are convinced of this because your free response here is a combination of this vector W by e to the power plus s and t. And so since you have this solution for the free problem, then stability is ensured by this poles or exponential characteristic of this equation. You know this, and so you have just to check this number. But now here you should do something similar. You should evaluate this P or this S, which is the same, by taking the determinant of P squared and A plus P and B. Okay, take this determinant plus C. Okay, do this. Okay, do this. Okay, this is complicated. Okay, do this. Okay, equal to 0. But are you again convinced that the solution is H and alpha of your problem is a combination of W, again this W, and by e to the power minus plus Pn by T? If yes, then it makes sense to evaluate this Pn again. The answer is yes. The free solution is again built in this way, and therefore Pn are significant for stability. Again, also if you have integral differential equation, no, it's okay. Pn are suitable to discuss stability. Okay, if you are in agreement with me on this point, you have understood 80% of an elasticity course are suitable to discuss the stability. And what about the difference between the standard situation of dynamical system and the aeroelastic situation? Yes, we have a more complicated problem for the eigenvalues, yes, but you have a generalized eigenproblem. Okay, call the problem how do you want to call? Okay, but the key point is that you have poles in the same way, but the only mathematical difference is the the presence of fundamental theorem of algebra. The fundamental theorem of algebra says that if you have a polynomial of degree n, then you have n root for such a polynomial. So how many are the poles for this system? If n, capital N, is the degree of the polynomial developing the determinant, you should have here, in the standard differential problem, you should have n roots, capital N roots. But in the case here of integral differential equation with the characteristic equation given by a transcendental equation, how many are the poles? How many are the roots of the determinant? How many roots this equation has? How many? How many Pn you have? You don't have only polynomial developing this determinant. You have something more complicated, because inside here, inside D, this is D, this is C, and this is D. You have a dependency on D, excuse me, as a function of P, not S. And this is C in your equation. Inside this D, we have a transcendental dependency on P. Okay? And what about the solution of this problem? How can we capture this pole? This is the point. I want to suspend this question, demonstrated later, probably next time. But I want to discuss with you the how find the poles of your system. And I want to see, yes, I want to take this here. How can we determine U flutter and P flutter equal to J K flutter? How can determine the value of the parameters U flutter and the value of the frequency of the margin pole here? Okay, if the point is continuation approach. In Italian, continuation approach is punto unito, metodi numerici. Assume that P is equal to JK, margin condition. So you want to find all the marginal value. You don't want to follow the root locus. We are just to find this situation. Limit condition. And the other point is the following. Assume Cp, a Taylor-Sand function C as a function of K, as separated variable. What does it mean, separated variable? An independent variable is not, we don't, in this point here, and here, we want to assume that this function, this p, which is, in this case, at limit is jk, this k is not this, is independent by this. Independent. And so assume an assigned value. Assume an assigned value. K bar. Okay? This equation, impose that the determinant of this equation is 0. Impose that determinant of this is 0. And look, develop this determinant ordering the final equation as a function of u, infinite. So write, if you see here, develop this determinant, you realize that you should have an equation, or a biquadratic equation in u infinite. So you have u fourth, a number, by a number, plus u to the power 2, a number, plus c equal to 0. But this number a is a complicated function of all the parameter, and is a complicated function of your k bar assumed value. Okay. When you write this determinant b equal to 0, you have satisfied the characteristic equation. You have satisfied, right? And you may evaluate for any value of k bar a value for u infinite to the power 2 by solving this biquadratic equation, which is your characteristic equation. So you have, but in general you have a complex number. So you have real part of u square, and you have an imaginary part of your root in u square. And you can write this real imaginary part as a function of the assigned k bar. What happens? You should have an imaginary part, curve, and you have a real part, curve, for any assigned k in this equation. Okay? Is u square a complex number? Not at all. Not at all. So when you have 0 imaginary part here, stop please. You have satisfied your characteristic equation. You have a 0 imaginary part for u square, and this u square here is your flutter velocity to the power 2. The value of k here that you have found here, which is by definition omega b divided by u. You have u, you have k, so you have omega. And you have finished because you have satisfied your characteristic equation. You have a physical solution for u, and you have closed your punto unito or continuation approach because you have establish that your K bar is now actually equal to omega b and by u. And so initially you assume that this was an independent parameter, but in this point here you have joined this parameter with its original meaning as equal to omega b by u infinite. Okay, and this is a continuation approach for solving the so-called flutter equation. We have the problem of the complexity of our characteristic equation, but we solve this characteristic equation in such a way. And this is very, very similar to what happens in the commercial code for evaluating the flutter. Stop here, please. And we go back to this point tomorrow. And this is the content of the exercise number 2 that I am going to assign to you. Do not be afraid. We go back to this content. We have to manipulate and elaborate this concept. And that's all for today. I will have with you another meeting tomorrow at 2 p.m. and thank you for your attention. As concerning the metrics, some metrics are rectangular